Hello, this is a demo video on ilogic rules in Inventor and weight and balances. Recently I started working on some custom ilogic rules to generate variables that I can then load into a weight and balance spreadsheet, an Excel spreadsheet basically. This is useful because in the past we've generated these spreadsheets manually, entered the weight and displacement of each object and position, and that's an awful lot of work. So being able to generate that directly from a Autodesk Inventor model is a very useful thing. The way we're going about business does not negate the old technique. It can be done in addition. In other words, you can generate a spreadsheet, 90% of a spreadsheet using the model, and then send your system out into the field and continue entering data into that spreadsheet manually, and just to keep it all updated. So to start with, we include some rules in the ilogic. There is a rule that we include at both the part and the assembly level, and that would be this weight and water rule, and we can just double click on that and the ilogic browser will come up. So for people unfamiliar with ilogic, well, I can't show that. I can show you where you get this from the ribbon in a second. Basically, this rule is pretty simple. It gets volume from the iproperties in Inventor proper, creates a displacement value by multiplying the volume by the weight of water per cubic inch, and it from there can use the mass of the object to generate a weight in water, and we basically create custom iproperty values, weight in water, weight in air, and displacement, using the standard Inventor iproperty values. So these custom iproperty values can then be later used in an Excel spreadsheet and or just put right into a drawing. So they're useful things to have, and they're useful things to know how you generate. And basically what happens is you create a variable. In this case, in this lower line, it's mass. We got mass right from Inventor. We just said mass equals iproperties mass, and we added this fixed thing. This fixed thing actually formats the output of the iproperties. We're basically keeping it to 2 decimal places here, and then that makes it easy to display later on in your drawing and or in a spreadsheet. So this, I mostly, with some help from online sources and from Paul Normand at Autodesk, generated this bit of code, and Autodesk, or Paul Normand at Autodesk, generated this much more sophisticated bit of code. This bit of code actually basically puts the geometric center of each part, this geometric center relative to the origin in the assembly, into each part, which is a very useful thing for us, and that's useful for putting the information into the spreadsheet. And it's also useful because you now have a fixed point that everything is measured to, basically. That allows us later on to add data into the spreadsheet manually. So you just have to be careful about how you choose that fixed point, and I'll go over that in a second. So this is that code. And now going backwards just a bit, you get to ilogic by going to the manage menu item, and then you go over here to add a rule. and this is the ilogic browser that puts this little cube up over here. And when you want to create a rule, you click on that. You can name the rule new rule, not rook, but rule, and you just say OK, and voila, this comes up. There's an awful lot of options here, and an awful lot of this is well beyond me. But there are wizards over here in the corner that allow you to create a rule for a dialog box. So you can have a dialog box come up and ask you all sorts of questions, and then put that information into parameters. The parameters can be turned into custom properties, so forth and so on. I did not, in this project, I did not deal with any parameters. I just basically took iproperties from Inventor, did some multiplication and some other little mathematic kinds of tricks, and then created some custom iproperties from there that I could then easily display. So that's how you get to the ilogic stuff, and there are many people who are very skilled at writing these ilogic rules. So if you're not skilled at writing or software and code, what you need to really know is that basically when you add a rule, this is text, so you can cut and paste text. You have to be careful about exactly where you get your text from, because oftentimes in word processors and whatnot, there's extra characters and things like that that are hidden and added in. But if you get a clean piece of text, you can just basically cut and paste a rule in and then use it for yourself. So making the Inventor software tremendously more flexible. I mean, basically it's now adapting to the customer's demands, so I think that's great. I've included this ilogic geometric center rule, which I only include in the assembly, and then it puts itself into all the parts, and then into all those parts it basically creates a set of custom iproperties that are X, Y, and Z values that are relative to this origin right here. And I'm going to open one of these parts. Okay, I've opened this cylinder. We're going to then find the iproperties, and we're going to go to custom iproperties. So this X, Y, and Z value is the geometric center of this cylinder relative to the origin in the assembly, not the part. So that's important, and that works great. The other values here are displacement, weight in air, and weight in water. These values were placed in by the weight in water rule or code, whatever you want to call it. Something important to note is you want all of your values to be numbers, and that way they'll go nicely into an Excel spreadsheet, and Excel can add, subtract, whatever, process them. When you make a part like the cylinder, it's important to include a material. In this cylinder, I chose titanium. It was already available, and this titanium has a mass and it has a volume, and that's what we're using with our ilogic rules. We're taking these masses and volumes with our ilogic rules and using them to create information for a spreadsheet that can determine basically the behavior of an object submerged, which is a weight and balance. So that means we've got stability information, the separation of the center of gravity and the center of buoyancy, and we also know whether the object will either sink or float, which is important. So one of the tricks to making this work is, we have this cylinder here, and in our world this would be a supported void. In other words, the water external to the cylinder would not go inside, right? And we have in the assembly, we have an end cap on this cylinder. We have the cylinder. So it's important to model the air inside that cylinder. So we're going to open up our little air model here. Okay, and this is what the air inside the cylinder looks like. So a couple of ways you can, there's some finesse here. First of all, you can just, if you have a simple shape, right, it's easy to just you know, make a part that is the same shape and size as the air volume. Now, if you have something very complicated inside the cylinder, like some electronics and circuit boards and chassis and so forth and so on, what you're probably going to want to do is derive this part. And what you do is you have a model of your electronics and your chassis, you have a model of your part model of your cylinder and end cap, and then you actually just take and you intersect those models with some simple shape, right? That simple shape is not the air volume, it's the air volume plus some extra. And then you open up another part, and in that part you derive. And so you can derive, say I want to derive something from this. Open. Okay, it's not going to let me. It's sorry, I made a mistake there. Say I want to derive, and this isn't a lesson on how to derive parts, but what you do is you can then derive the air volume. It'll be the spaces in between the other parts in your assembly, basically, and that works well. In my case, I didn't do that. Everything was simple here. I just pulled this out of a master sketch, okay, and I got this volume, and then I went to the styles editor and I created this density for air as a material. So basically this is the density of air. I've applied that and I've made it glass because air is clear or whatever. So basically this gives me, that makes a nice pure air volume. Now I did one thing a little bit extra, right? So oftentimes when you're making larger complicated models, you don't want to put all the chassis components, the resistors, the circuit boards, whatever, inside a pressure housing that's a supported void. It's too much. You don't want that level of detail. And so how do you get around that? Well, in this case, you'll notice the name of my thing is air volume component mass, right? So Inventor allows you to fudge the iproperties, and that's what I did. So basically, I gave this air volume, which has some very small amount of mass. I wrote in 25 pounds because I'm pretending that I have 25 pounds of internal components, okay? And I just wrote that in. You see this little hand here instead of a calculator. This hand means that I have fudged that value. I've manually put in a value. And so that's a way to simplify your models, but still get all the data that you require in terms of displacement and mass and so forth and so on. So that's what I've done there. And so I'm going to close this out, and we're back to things. So good, we've got a model. It's got a bunch of custom iproperties in it, and we've generated those iproperties using these ilogic rules. And so, you know, the reason we're doing that is because we want to be able to get to this data. And so how you get to this data is you can, one, just simply display it via a text box. Here's a text box. And we're going to open that up. So here's a text box that could go in a drawing. You have weight in air, you have weight in water. You know what your design is basically doing when it's submerged. You get these iproperties by going to Custom iProperties Model, and you go over here and displacement has come up. I don't have displacement here, so let's just put displacement right in there. So by clicking on this little add a text parameter, these really aren't parameters, they're really custom iproperties, but it does the trick. And down it goes, we say okay, and there you go, that's the displacement right there. in pounds. So we don't need the displacement. That's how you go about business there. It's very straightforward. Your variables will, once you choose custom iProperties over here, custom properties models, your variables will come up in a list and you can choose from them. Good. So now so that's useful all unto itself, and that was actually my original goal. But I kept going with it, and I got some help from Autodesk to keep going with it, and I think this is wonderful. And it does need a little more testing than what I've done currently, but this is a great start. The other thing that you can do is you can generate a parts list that has your, in this case it's weight and air, displacement, X, Y, and Z for each of the parts relative to the origin in the assembly. So the way you do that is you go to your bill of materials. Now you can go to your bill of materials in your IDW, you can go to your bill of materials in your assembly. And here it comes up. And so we've written the ilogic rules, we've made custom iProperties equal to variables within those rules, and those custom iProperties come up in the iProperties menu. You can then go here in your bill of materials to add a custom iProperties column, and you click on that, and here these are the custom iProperties that I have included. The way you add a custom iProperty is you click on add a custom iProperty, and you type in the variable. Now you have to know, at least to some degree, what your variable is. Once I typed in the capital W, weight and water came up. It could be, I could be putting weight and air, so forth and so on, and you can add them in. Actually, you can choose some of them. But you have to start with something that exists. In other words, if there wasn't a capital W in one of the variables, you'd be kind of lost. So I don't want the weight and water, so I'm just going to cancel out of this. So I added those in, I formatted everything. I've got weight and air, displacement, X, Y, and Z. I line things up like this because that's how I'm going to use it in my spreadsheet. You'll see that in a second. So you can actually, going back to the, let's see if I can make this work. Bill of materials, we're going back. You can export this. I don't export it here because there's a lot of extra information I don't want to go into my spreadsheet. Just makes life more complicated. You export it from the parts list proper. So you make your parts list, edit parts list. You make your parts list by using a column chooser, and I chose part number, weight and air, displacement, X, Y, and Z. Obviously you can change this around by adding and subtracting from one place to the other. The way you get custom iProperties though is you have to go to new property, click here to add the new property, then you type in the variable name. And again, you have to know the variable name to get it to come through. This won't even work from a prompt. You have to, if you got weight in air, you have to be able to type in weight in air with it's case sensitive, so forth and so on. So pay attention a little bit there. Great. So these are the selected columns. They're custom iProperties, and they have the weight and balance information that I want in them. So then, again, I'm moving along faster than I'm. So after you get your parts list formatted like this, or something similar to this, depending on how you're going to generate your Excel spreadsheet, you go to export, and it's important that you export as a comma delimited file So that's a CSV file right here. I've already exported it, and it's gone out here as sample weight and balance. So I'm not going to do it again, but that's what you do. You make sure that you export it as a CSV file. And under the options, is nice is if you've got a little extraneous data, for instance, say you have more information in your parts list, you know, maybe ordering information, so forth and so on, that's not purely a weight and balance. You can select and deselect items here in the options. You also have some formatting tricks here, none of which I required for my simple situation here, but very well may be useful to you. Okay, so I've created a drawing that's got a list that's basically a weight and balance list, and a text box. So what do I do from here? Well, what we can do from here is import that data into an Excel spreadsheet. This is a spreadsheet I made quite some time ago that basically takes an object, its weight in air, the amount of water it displaces, its position. It creates moments from there. You can sum those moments, excuse me, and create a center of buoyancy information, center of gravity information, separation between those things, forces acting to this force here, the center buoyancy force, is actually the water that's totally been displaced, and this is meaning that it's not the actual buoyancy. Over here is the net buoyancy, which is the actual buoyancy of the object. Could be a negative number as well. You'll notice that this number, this 1249, is the same as this 1249 number. This is a negative number because this is the weight in water and the other is buoyancy. They're inverses of each other. So, and then from there, actually, I create an angle in X and Y and an angle in Z and Y. And I've put in a few notes about what these values indicate. So positive value indicates upright position, and so that's why and this X, Y, and Z information and this information, for it to be meaningful, everybody has to be decided on where the origin is, where all this X, Y, and Z information comes from. And so traditionally it's been from the front and to the bottom. So that's the way I've set up this particular situation. And then we've simply made a graph, and we put an image in the back of this graph, and you can see here that the center of buoyancy and the center of gravity are not directly over each other, meaning that this object's going to shift in this direction, which, if I am right, and I'm going to check, it's like it's easy to get confused. The positive value indicates roll to starboard. So 0.41 is a positive value, and so if you turned yourself around and this was the front, you would see that this would be the right side, although it's your left side now, and that this thing would be rolling to starboard. And then so here's the same, this is the front over here, and you know, you can see that the center of buoyancy and the center of gravity are not right over each other, meaning this object is going to rotate. And if we go back here, we can see that there's a negative angle of 24 degrees, so it's actually going to rotate quite a bit. So there isn't a great separation between buoyancy and gravity here. 5 inches is probably way more than enough for most people's situations. But anyways, that's the information we're generating. And you know, what's really critical is the net buoyancy. Obviously, you want many things that go under the ocean, neutrally buoyant, and this allows you pretty accurate mechanism to understand when you've got there. Let's see, what else do I need to see? Oh, I need to tell you how we get the data into the spreadsheet. So we've generated data with a parts list, and we generated it as a .csv file, right? So you go to the data tab on the top here. You want it from text. It's essentially text information. You say OK, and that's my data. And we want delimited data. Hit next. We don't want tab. You do want comma, and that lines up our rows and everything nicely. Okay. And then next. You want general, and you say finish. Now I'm not going to put this data into here. I can go one step farther. So where you want to put the data is in this particular spreadsheet. It's A8, and the reason that that's good is the parts list sends over this first row. Okay, and this first row, the information here is not formatted the same, okay? But it's nice to have this first row because we know that the description and the part number go together, the weight and air go with weight and air, displacement, X, Y, and Z. So lets you know all the information is lined up. All this from here on over, you can see is calculated. So basically, is that really subtraction? That may not be. Oh, you know what I'm doing? Sorry, I'm making an error here. So I will go back. Basically, where you want to insert your data is here, because over here is calculated. And from this point on down, basically it's taking the information out of your spreadsheet. This is the header. I want to cancel out of this. So these columns over here are calculated, and indeed they are multiplied, not subtracted, so I don't have to freak out. Good. So that's how you get the data in. Staying on topic here, we've talked about the reference point, we talked about exporting, we talked about Excel spreadsheet, we've talked about Autodesk generating a wonderful rule that calculates the geometric center of each part, reference to the origin and the assembly, and wanted to say thank you. And I think that's it. So I think with that I will be on my way. I'm going to send out these files and this information, and I hope you all find it useful.